Hello everyone and welcome back to another video. Today we're going to be looking at the topic of electromagnetism. As always, if you'd like to give any of these questions a go, please pause the video and I'm going to do the answers in 3, 2, 1. The magnetic flux linkage through a coil depends on the thickness of the wire, the angle between the coil and the magnetic field, the angle of the direction of the magnetic field, or D, the material the coil is made of. So this is pretty much a theory question, but you could also do it if you know how to interpret the formula. So magnetic flux linkage is given by the formula phi, or it's given the symbol phi. And if you check on your data sheet, phi is equal to B times A times cos theta, right? Now, B is the strength of the magnet, right? So strong magnet, weak magnet. A is the area, and cos theta is that, so theta specifically is the angle between the coil and the magnetic field. So just on interpreting the formula, we can conclude that the answer is B. Let's move on. Question number 6. So question number 6 reads, a coil with a diameter of 0.6 meters contains 60 turns and lies so that the magnetic field strength is at its maximum of 0.15 T. The field then changes to its minimum in 1.6 seconds. They tell us the formula for area. They've been kind enough to do that for the coil, pi r squared. 6.2.1, calculate the change in magnetic flux in the loop. So basically they want the delta phi. So delta phi, that's equal to phi final minus phi initial. All right, now let's think about it. The field changes to a minimum in 1.6 seconds. If it's difficult for you to interpret it or to imagine it, let's use a diagram. So we start off, let's say the magnetic field is going this way, right? And they tell us that it's at its maximum. It's at its maximum, meaning that the coil actually looks like this. And this magnetic field is going through the coil, right? Now that means that the theta, the angle, is going to equal 0 degrees. And why is it 0 degrees? It's 0 degrees because when you think about the angle, you're not thinking about the actual angle of the coil itself. It is the angle that the magnet or the magnetic field makes with the normal of the coil. So the normal of the coil would actually go to the right or to the left. And that means the angle is then theta. Okay, so just remember that the theta angle is actually the angle that the magnetic field makes to the normal of the coil, not the coil itself. Okay, so when it's like this, that's when you're going to get a maximum. But when it rotates, meaning when it looks like this, when the magnetic field is like this, but now the coil is like this, that means the normal of the coil is actually pointing up or pointing down. And then the angle here is going to be 90 degrees. That's when you're going to have a minimum. Okay. Now, let's go back to our formula. So delta phi is equal to the phi final minus phi initial. Now we can calculate this. We can say, so we're skipping from here, we're going there. So this is going to be BA cos theta, and this is final, minus BA cos theta, and this is going to be initial. Now, we know the strength of the magnetic field. They tell us it's 0.15. So 0.15. And then the area they tell us is pi r squared. If the diameter is 0.6, that means the radius is 0.3. So 0.3 squared. And now we're going to have cos of 90 degrees. Right? Because remember, when it's at a minimum, right? Remember, it went from a maximum to a minimum. So this is the final. This is the initial. Right? Then we have minus 0.15. Then pi times 0.3 squared. And then cos of 0 degrees. And if you put that in the calculator, cos of 90 is 0. So this entire thing here is 0. So the final answer is going to be minus 4.24 times 10 to the minus 2 WB. So remember, phi of magnetic flux is measured in Webers, so WB. Okay, let's move on. Question 6.2.2, calculate the average induced EMF in the loop in 1.6 seconds. Okay, so next one, 6.2.2. Let's think about what we have. We know that the time is 1.6. We know delta phi is minus 4.24 times 10 to the negative 2. We also know the number of loops. They tell us that there are 60 turns. So they want EMF. So we go to our data sheet and we find the formula. The formula is EMF equals minus n times delta phi over delta t. Now we substitute minus 60, open bracket, minus 4.24 times 10 to the negative 2 divided by 1,6. And that gives us a final answer of 1,59 volts. Okay, last question. If the coil is now rotated in 1.8 seconds, how would this change affect the EMF? Write down increase, decrease, remain the same, and explain. All right, let's look at our formula, 6.3. So EMF is equal to minus n times delta phi divided by delta t. Right? Now, delta t is in the denominator, meaning, and this tells us that the EMF is going to be inversely proportional to time. That means if the time increases, the EMF is going to decrease. Okay, and that's it for this section. If you've liked this video, we found it useful, please consider leaving a like. If there's something you want me to do specifically, a specific question, specific topic, please let me know down in the comment section below. Until the next time.